Okay, we are on lesson 5 of unit 3, evaluating logarithms. And here's a little review of the last lesson that we had. In the last lesson we compared these two graphs, and we saw, for example, that if we have y equals 2 to the x, then we could inverse that if we want and take the x here. We can, let's take that again. X would equal 2 to the y, and we can write that in logarithmic form now that we have the inverse. We can log the x, this is the base of 2, and it equals the exponent, which is y. So in fact, this is the same equation. These are inverses of each other. Now, if the point 38 lies in the graph of this, then the point 83 lies on this graph, because these two are inverses of each other. This simply indicates that if x is 3, y is 8. And here it simply indicates that if x is 8, y is 3, in this fashion right here. The exponential form 8 equals 2 to the 3, and the logarithmic form 3 equals log 8 base 2 are equivalent. And in this lesson we will learn how to evaluate logs like this, without reference to a graph or a table. Well, one way to do this is by evaluating logs by converting to exponential form. Kelsey was asked to evaluate this, and her work is shown below. Fair enough. She sets the log to a specific value, and to use v for value. So log 8 base 2 has a particular value, and that's exactly what we're looking for, this value. What does log 8 base 2 equal? Well, if we change it to exponent form, we know that we can do drop, swing, bump, drop the 8 down, swing the 2 over, and bump the v up. So the 8 drop down would equal 2 to the v. So here we are here. Now, if we make a comparison, or a common base, 8 is really 2 to the 3. So we can see that v actually equals 3. So this log 8 base 2 is actually 3. Okay, evaluate the following logarithms. Here we can do drop, swing, bump. Log of 81 base 3 has a value, and if we drop the 81 down and bump, swing the 3 over, bumping the v up, we get this equation here. So 81 is 3 to the 4, and that means v has to be 4. Same goes here, drop, swing, bump. 64 goes down, the 4 swings over and bumps the v up. And 64 can be written as 4 to the 3, so v must be 3. Drop, swing, bump. 7 goes down, 7 swings over to bump the v up. So we can see v has to be 1. Notice that log 7 base 7 is 1, and we'll come across that again. In fact, if we have log 82 to base 82, that still equals 1. Log 1 base 12 equals v for a value. We drop the 1 down, swing the v over, swing the 12 over, bump the v up. 1 is 12 to the v, and the only time this could be equal to 1 is if v is 0. Okay, so v is 0. Okay, here we're being asked to determine the value of log 1 to the base b. The value is v. Drop the 1 down, the b swings over and bumps the v up, so 1 equals b to the v. And the only time this would equal 1 is if we had an exponent of 0. Anything to the exponent 0 equals 1, so v must be 0. Over here, as I mentioned before, when you have a log of b base b, it equals 1. So let's drop the b down, swing the b over and bump the v up. We have b equals b to the v, so v has to be 1. Let's evaluate these logs here. They have a value, set it to v. So to convert to exponential form, we drop the 512 down like this. The 8 swings over and bumps. Oh, sorry, I forgot this 2 in here. So we really need the log by itself. It's been multiplied by 2 here. Before we do a drop, swing, bump, we must take account for that. Well, 2 ways of doing it. This is one way. We bring the 2 over, we divide both sides by 2. And now we can drop and swing the 8 over, bumping this up. It's probably the easiest way to do it. And therefore, we should try and write 512 to a base, a common base, such as 8. And it actually is 8 to the 3. So 3 equals v over 2. Multiply both sides by 2, we get v equals 6. So the log of 2 log of 512 base 8 is actually 6, taking our cue from what we had up here. Again, you can do drop, swing, bump. There's nothing multiplying out front, so drop the 1 over 32, swing the 2 over, bump the v up. Now this has got a base 2, this has not, but we know this is really 1 over 2 to the 5 or 2 to the negative 5, so v is negative 5. So this has a value of negative 5. Now when we can't come to square roots or even cube roots, we've got to change this sign, this radicand sign, into an exponent. So if it's a square root, it's 1 over 2. If it's a cube root, it'd be 1 over 3, and so on. So we really can again drop this down, swing the 5 over, bump the v up, and now we can write this as 125 to a half. Changing the 125 to 5 to the third, these two exponents multiply, giving 3 over 2, and so 3 over 2 must equal v, so this whole thing equals 3 over 2. Okay, in the next example, it's asking you to evaluate 5, and now the log is actually in the exponent. So again, this has a value, so we can set it equal to v, as we do down here. Again, we can drop the 25 down, and the 5, the base swings over and bumps the v up. So this is sort of written backwards from the way we've been doing it before. The v has actually been over here, and we've been dropping the 25 down and swinging the 5 over, bumping the v up. Okay, so we can see that 25 is really 5 to the 2, so v has to be 2. Okay. Now, notice what we did. We evaluated the exponent here. We didn't evaluate the whole thing yet. We evaluated the exponent. The exponent, this log 25 base 5 that we have up here, is actually equal to 2. So we can rewrite this as 5 to the 2, which equals 25. Another way to look at this, and I'll probably say down below, is that this is really equal to 5 to the log base 5, 5 to the 2, oops, seem to have cleared that. Okay, let's write it down here. Oh dear. Just bear with me a minute. Here we go. So as we write it 5 and the exponent is log 5 base 5, now notice 25 I've written as 5 to the 2. Okay. Now when we have this situation log 5 base 5 and the 5 here is raised to the 2, this whole thing here becomes 2. And we'll see that down here when we get further on. Well, anyway, looking at the next one, Again, we can evaluate, first of all, what is the value of the exponent. So log 49 base 7 has a value, and we're going to find out what it is. We can drop the 49 down, swing the 7 over, and bump the v up. So we get this. So we know really that v has to be 2. So really we're dealing with 7 to the 2, or 49. And this is a very similar one. I won't go over it with you. Based on your observations from A to C, what is the value of this here? Well, notice in all these examples we have 5 and we have 5, we have 7 and base 7, and 3 and 3. We find that A to the exponent log n base A actually equals n. Okay. Notice this 25 is 25, this 49 is 49, the 27, 27. So raising a base to a power and taking the logarithm to the same base are actually inverse operations. Raising a base, here's the base A, but here's the base we're raising to a power, and taking the log of this to the same base, they're basically inverse operations. Here we'll do it over here at step. Here's a base, and I'm going to use this as a base, and raising it to a power, and then taking the log of this to the same base, base A, that actually equals, it's inverse operations, it equals n. And that's what's being stated right here. Here we're going to evaluate logs by changing the base. Now, try to evaluate log 50 to the base 5. What problem do you encounter? Well, let's just set this to a value, v, and this 50 comes down and 5 swings over and bumps the v up. 50 equals 5 to the v. Can we write 50 as a power of 5? No. 5 to the 2 is 25, 5 to the 3 is 125, and so on. So we cannot express 50 exactly as a power of 5, it says here. Part B, choose the correct alternative. The exact value of this is, well, it's between, because of what we've seen here, it's between 2 and 2.5. It's between this and this. Okay. Now at the moment we're able to evaluate, unable to evaluate this log by converting to exponential form. However, we can evaluate the logarithm using a calculator by changing the base to a base the calculator recognizes. Okay, so to do this we introduce what's called common logs or natural logarithms. In our calculator, normally when we take a log of something, we take it, the common logarithm in our calculator, we are using a base 10. So if we log 1,000, the calculator says, oh, we're using base 10 automatically. We would have to specify a different base if we wanted to. But our calculator right now, whenever we punch in log of 1,000, it will take the base to be automatically, or punch in whatever number and log it, it's taking a base of 10. So these logs are in such common use that when a base is not given, the log is understood to be in base 10. So we typically can write log of 1,000 base 10 as just log of 1,000. It's assumed the base is 10. So on a graphing calculator, this can be evaluated just by simply using the log key. So evaluating log of 1,000, we just punch it in, we go log of 1,000 on our calculator, and it spits out the number 3. Or we could do it ourselves. We could drop the 1,000 down, swing the 10 over, bump the v up, drop, swing, bump, and we know that v has to be 3. Doing the same on a calculator will get you 3. Now in each of the following, estimate the value to the nearest whole number without using technology and explain your reasoning. Also approximate the value to the nearest 100th using technology. Fair enough, we're taking log of 89 to the base 10. We can do the drop, swing, bump method. this equals a value, and so we drop the 89 down by itself and swing the 10 over, bumping the V up. So 89 is a power 10 to what power, or what exponent? Well, it's close to 2, it must be less than 2, so estimate 1.95 perhaps. Try that on the calculator and what do you get? If we take log of 2000, again 2000 would equal, base 10 is not really put in here, but it is base 10, and this is a value, so we swing the 10 over and bump the V up. If V is 3, we know we've got 1000. If V is 4, we know we've got 10,000. So it's way closer to 3 than it is to 4. So 3.3 is an estimate of the value. Looking at natural logarithms, natural logarithms have a base of e, and e just is like pi. It has a certain value. If you read below, down here in your book, you'll see some more information about the value of e. And if we use base e, we are using what's called natural logarithms. Okay, e is an irrational number, very much like pi, the value of which can be determined below. Log 15, base e is often written as ln 15, and I'll refer to it when I speak of this as ln 15, rather than log 15. So in the graphing calculator, use the ln key. Evaluate the following logs to one decimal place when necessary. Now when I say decimal places, typically you'll be using your calculator. So all you have to do is punch in ln5 or ln5 and you get the answer. And notice if you use log 5 base e, how do we get that? How do we get that with punching in that into the calculator? Well, because we can't really tell the calculator what base it is, we don't know how to do that as yet, but we'll see shortly how to do that. Calculator, when we use a log, typically thinks the base is 10. Let's see if we can help ourselves by setting this value to v and dropping the 5 down, putting the e over to the other side and bumping the v up. If you see below the value of v, I can't remember what it is offhand, I don't have my book with me, but is it 2 point something or 1 point something, I can't remember. But if you punch it in and just guess and check with values of v, what value of v will equal 5, and you can see it's 1.6. Natural log or ln of the value or the constant e, basically these are inverses of each other, you get the value 1. It's a bit like taking the log of 10 when the base is 10, you get 1. Okay, so what's happening here when we say this, really, just tell you that ln of e is really written with a base 10, or sorry, written, with a log. It's log of e to the base e. That's really what ln e represents. So again, we can see that it equals, from previous examples, we know that equals 1. So please read through this enrichment section talking about the approximation of the value of e. And I'm split this lesson into 2 parts, 2 videos, and so this is the end of part 1, and I'll make part 2 on the next page.